Welcome back. Let us now continue our discussion with few more examples. Let us consider this problem. The argument which is passed to this function is n, and this function has one loop, and this is a sequence block. So every iterations of this is a basic steps requiring 1 unit of time, and this is a sequence block, so we can consider the sequence block is requiring 1 unit of time. Now in this case we can say what is the total count for this is n, and for every iteration this sequence block is executed, so this will also take n unit of time. So total time Tn, that can be said as 2n. So from our previous discussions we can say Tn is theta n, because the time, because this is both upper bound as well as lower bound. Let us come to the second problem, where there are nested loop and the executions of the inner loop does not depends on the execution of the outer loop. So we can say that this is executed how many times? Number of iterations of the outer loop multiplied by the number of iterations of the inner loop, or we can count the total number of times this is executed. So this iterates n times, this iterates n squared times, and this executed n squared times. So the total time here Tn, that is 2n square plus n. Now in this case we can say that the behavior of this function is depending on n square, not n, because for larger values of n, n square dominates over n. So from the same analysis we can say that Tn is equal to theta n square. Now why theta n square? Because we can say Tn is equal to both big O n square and big omega n square. Logic is very simple. Let us quickly brush it up. We can write Tn is equal to, as it is given, 2n square plus n. So we can write Tn is less equal to 2n square plus n square, even if n greater or equal to 1. So we can say Tn is less equal to 3n square for n greater or equal to 1. So this is our C and this is our n0. So from this we can say Tn is equal to big O n square. In the same way, from this Tn is equal to 2n square plus n, we can write Tn is greater than or equal to n square, 1 n square, even for n greater or equal to 1. So in this case this is my C and this is my n0. So we say Fn, that is in this case Tn, is greater or equal to C into Gn. So from this we can write Tn is equal to big omega n square. So both big omega and big O both exist, as both big O big omega exist. So the accurate or more deserving analysis for Tn is theta n square. Now let us consider these two problems. This problem came in gate 91. So this is a basic step requiring 1 unit of time. Every iterations of this loop, condition checking and these computations is a basic steps requiring 1 unit of time, and this also requiring 1 unit of time, and this return statement requiring 1 unit of time. Now see how many times this while loop is iterated. So for I is equal to 0, 0 into 0 is less than equal to m. After that I is incremented. So in this way it will continue. So when the value of I is say k, okay, then the value of k is such that k square is less equal to, that is k square is less equal to m. So we can say k is, okay, equal to root over of m. So this will iterates root over of m times. So this will also iterates root over of m times, that is k times. This will also iterate k times, and this will execute 1 times. So we can say the total time Tn, that is equal to 2 root m, this one, plus this will take 1 unit and this will take 1 unit, plus 2. So from the same concept we can say this is theta of root m. Okay. Let us consider this one. It is almost same problem formation with a slight modification, slight changes. Here S is the sum which is calculated. It is summed up I times. This I is every time added, and I is incremented every time once. So this will executed only once. So this will consume 1 unit of time. Now how many times this will be executed? This will be iterated. So this will be iterated for when I is equal to 1. In that case, the value of S, here I is first incremented, so S will be, okay, incremented by 2, that is S is 1 plus 2. For I is equal to 1, let n is given here. So S is less equal to n, this is calculated. So in this way it will continue. Suppose it will continue till this time S is equal to 1 plus 2 plus 3 plus dot dot plus when the value of I is n. In that case, okay, let the value of I is up to k. Now when this sum is up to this, then this sum will be such that S must be less equal to that n. So whenever the value of S exceeds that value, then it will stop. Now what is the value of this sum? S is here, this can be said as k into k plus 1 by 2. So the value of, okay, so the value of k will be such that k into k plus 1 by 2, that must be less equal to n. So here this term is k square plus k divided by 2, that is less equal to n, till that this loop is iterated. So whenever this value k square plus k divided by 2 is greater than n, then it will stop. So the value of k is again of the order of root over n. So again here there are some other terms. So we can say this running time for this algorithms is P go root over n. Okay. Okay, let us consider these two problems. In this case, there are two loops nested, but the inner loop depends on the iterations of the outer loop. So we cannot simply multiply the iterations of the outer loop and the inner loop to calculate the running time for this program part. So we require to unroll the inner loop. Let us apply the same technique here. Every iteration is a basic step, so this will take 1 unit of time. Again, every iteration here is a basic step, basic computational task, so requiring 1 unit of time. And this is a sequence block from our previous discussions that will also take 1 unit of time. And this will take how much units? This will take n units, total n units, because for I is equal to 1 to n, this will consume n units. Now, how much time this inner loop will take? For I is equal to 1, this loop will go from I is equal to 1 to 1 times. For I is equal to 2, j is equal to 1 and j is equal to 2. So 2 times this will be executed. So in this way, for I is equal to n, this will be executing from 1 to n, that is n times. So that is the number of iterations of the inner loop. So this comes to n into n plus 1 by 2, and for this will be also iterating n into n plus 1 by 2. So the total time Tn is this plus this, that is n into n plus 1 by 2 into 2, that is n into n plus 1 plus n. So this comes as n square plus 2n. So as per our previous discussions, so we can say this is nothing but, in asymptotic notations, this is nothing but theta n square. Now let us come to the next problem, which is slight modifications of the previous one. Here there are 3 loops. The loop controlled by j is depending on I, but k is independent of both I and j, and this iterates fixed number of times, c times. C is a fixed number, 50. So from these previous examples, we can say this iterates n times, this iterates n into n plus 1 by 2 times. But irrespective of this j, this will iterate c times, c is here 50. So how much time this will take? How much unit of time this will take? That is 50 into this value. Let this value is x. So 50 into x. This will also take 50 into x. X is nothing but n into n plus 1 by 2. So what is the total time here? Tn. That is, if you add all these things, it will be 50 into n into n plus 1 by 2, okay, into 2, that is we are counting this as 2, so this into 2, this one, plus this amount n into n plus 1 by 2 plus this one n. So that is the total time. So we can say this is nothing but 50 plus this one n plus 1 by 2. So roughly plus this n. So this can be said as n square plus n by 2 into 101 plus n. So in this case, the dominating term is again n square, because ultimately it will give you a equations which is dominating term is n square. So again we can say the running time for this is theta n square. So very important point to observe from here, that though there are nested loops of 3 times, so this contribution is constant, because this is iterated constant amount of time. So in this case, though it is a loop, but it is not influencing in the overall time, only it is increasing the count slight by constant amount. So, in order notations, again this running time is n square, same as this. But if instead of C, if this runs for n times, then what happens? In that case, the running time will be changed, like total time will be order of n cube. You just observe from here, this is n times, this is iterating n into n plus 1 by 2 times, and this is iterating n times, this is also n times. So, as a whole this will take n into n plus 1 by 2 into n, and this will also take n into n plus 1 by 2 into n. So, this is nothing but n plus n square plus n by 2 plus this is order of n cube. So, this is n cube plus n square by 2 into this is also n cube plus n square by 2. So, we can remove these 2. So, this is n cube plus n square. So, in this case, which is the dominating term? Dominating term is n cube. So, for larger value of n, n cube is growing much faster than n square. So, dominating term is here n cube. So, continuing our previous discussions, we can say the running time of that is theta n cube. So, that is the main concept lies in asymptotic notations. We are ignoring the constant because constant are dropped as in the same way the higher order terms dominating the lower order terms, because in this case there are both n square, n and constant terms as well as n cube term, because n cube, n square and n, all these things will not be that much dominant as compared to n cube. So, for larger values of n, n cube is the dominating term. So, we can say running time for that is be n cube if C is replaced by some input parameter n.